the Lord God Almighty, was and is to come. With all creation I sing praise to the King of Kings. You are my everything, and I will adore you. Amen. Beautiful voices, Turkey. You may be seated.
Well, welcome again for our last session. The secret code of creation. The secret code. So we're going to have to swear you to secrecy, and you're not allowed to tell this to anybody because it's a secret. Well, it won't be a secret after today. So just want to remind you, there's some giveaway things in the lobby. The stuff in the lobby table is free for the taking. And we also have our little Calvary Chapel bookstore down by the kitchen. It's to the right when you go downstairs. And there's a few different titles down there you might find appealing. Take a look if you're interested. So when this session is over, we're going to have a closing song. And while we're singing the closing song, I think they're going to put the food out. So hopefully when we're done this session, we'll pretty quickly be able to eat our lunch. So here's Jason for the secret code.
All right, this is a fun one. When I learned the information I'm going to share with you today, my mind was blown. I hope yours will be too. You can imagine if we found a secret code in numbers, what would that mean? Like numbers, 1, 2, 3, 4. What if we, in searching through these numbers, we found sort of a secret message in there? That would be wild, wouldn't it? Because who made numbers? Well, you know, a lot of times people think, well, people made numbers. No, we invented the notation. We decided 2 should look like that and so on. But numbers existed before people because remember, the way the planets orbit involves numbers, and planets orbited perfectly well before people, for 2 days anyway, right? So numbers predate people. And who determines the relationship between numbers? Like, who decided 2 + 2 should equal 4? I mean, we observe that it does. We've discovered that, but who made that rule? It wasn't people. And of course, I'm going to argue that God is responsible for numbers. We don't think about God creating numbers. We think about God creating the earth and the stars and animals, and of course He did, human beings. But God's also responsible for abstract truths like laws of logic or laws of mathematics, the relationship between numbers. The reason 2 + 2 = 4 is because that is true to the mind of God. And what we're going to see today is that there is, in fact, a secret code built into numbers. It's been there since creation. And we only discovered it about 40 years ago. So this was totally unknown to our ancestors. Totally unknown. And we'll see why that is. And I have to tell you, when I was a little boy, and my mother would prepare these wonderful meals, but occasionally she would put broccoli on my plate. Yuck. And the rule was you had to eat everything on your plate before you could be excused. And so I knew I was going to have to eat that broccoli. And occasionally, in rare moments of maturity, I would eat the broccoli first, get it out of the way so that I could then enjoy the rest of the meal. You know what I'm talking about? Yeah. Well, in that spirit, we got a little broccoli to do first, okay? But stay with me because it's going to get really cool. And if you skip the broccoli, you won't be able to enjoy the rest of it because you won't know what it means. So follow me here. We're going to start with what we call sets. In mathematics, a set is a collection of elements with a common defined property. And so in this case, a set of numbers. And in most sets, some numbers are included while other numbers are excluded. Although you could have the set of all numbers or the set of no numbers, that's fine. But in most sets, some numbers belong and others don't. So for example, consider the set of even numbers, those numbers that are evenly divisible by 2. Which numbers would belong? Well, these ones would belong, wouldn't they? They're part of that set, and the other numbers would be excluded from that set. That's pretty easy. That's a set, the set of even numbers. A different set will have different numbers in it. Consider the set of negative numbers. And that would have all these guys, right? And it would exclude all the others. So now with those two sets, the set of even numbers and the set of negative numbers, you can tell just by looking at the number whether or not it belongs to the set, can't you? If it's even, well, it's okay. It'd have to end in 0, 2, 4, 6, or 8, and it belongs. If it's negative, I just look and see if there's a little minus sign in front of the number, and if there is, it belongs. And if not, it doesn't. That's pretty easy. There are some sets where you can't tell just by looking at the number whether it belongs, because the definition of the set's a little more complicated. You have to do a little bit of work to find out if it belongs. We're going to talk about a specific set today called the Mandelbrot set. And it's one of those ones where you can't tell just by looking at a number whether it belongs. You're going to have to do a little bit of work. The Mandelbrot set is defined as the set of all numbers, lowercase c. C is a candidate for the Mandelbrot set, okay? For which the sequence of z, which is a different number, remains small according to this little formula. Now z sub n means that there's many z's. There's a z1, there's a z2, there's a z3, and z4, and each one of those is a number, okay? And we find that when we run the numbers through that little equation, starting with our particular z, which always starts as 0, and then you add it to c, the number we're checking to see if it belongs to the Mandelbrot set, you'll get a new z, which you're then going to put back in and do it again and do it again and do it again, and it'll generate a sequence of numbers. And one of two things will happen. Either that sequence will remain small, or it won't. It'll get bigger and bigger and bigger. One of those two will happen. And if it gets bigger and bigger and bigger, then C is not part of the Mandelbrot set. But if it stays small, let's say less than 10, then C is part of the Mandelbrot set. Okay, now that sounds complicated, but let's do a couple of examples, and it's pretty straightforward, really. We're going to ask, is the number 1 part of the Mandelbrot set? So C is 1, because that's the number we're checking to see if it belongs. And so C, we're going to put 1 in for C. And so there's our little formula. N plus 1 just means the next value of z, right? So z always starts as 0. That's the first value of z. So we're going to put 0 in there. 0 squared, 0 times itself is 0. Plus 1 is 1. Okay? So that's our new value of z. So we're going to record that down there. That's our new value of z, okay? Now we're going to take that new value of z and plug it back in. See? So now we've got 1 squared. 1 times 1 is 1. Plus 1 is 2. Good. Pretty easy. Now that's our next value. So we're going to put that back in. 2 squared, 2 times 2 would be 4. Plus 1 is 5. Good. Put that back in. 5 squared would be 25. Plus 1 would be 26. See what's happening there? Put 26 in. That's going to give you a big number, right? And so on. Now, we don't really have to do any more because we can see what's happening. It's going up. Is the value of C remaining, or is the value of Z remaining small? No. So is the number 1 part of the Mandelbrot set? No. Because the sequence did not stay small, it got big. Okay? So we checked the number 1 and we found it did not belong to the Mandelbrot set. Let's do one more. Let's do negative 1. So Z squared minus 1 now is the new value of Z. Z always starts as 0 by definition. So we have 0 squared, which is 0, minus 1 would be negative 1. Okay, we put that back in. Now negative 1 squared would be what? 1, would be 1. Minus 1 would be 0. Oh, put that back in. This looks familiar. 0 squared minus 1 would be negative 1. See what's happening there? 0, negative 1, 0, negative 1, 0, negative 1. Is it staying small? Yes. So is negative 1 part of the Mandelbrot set? Yes. You got it. It's that easy. It's tedious, but it's easy. Okay? We could do 0. You'd find 0 just generates a list of zeros. So 0 belongs. So we've checked 3 points. 1 does not belong. 0 does. Negative 1 does. And mathematicians were a little puzzled by this because they found that sometimes 2 numbers that are right next to each other, one will belong and the other won't. It was a little surprising that you could have 2 numbers so close and yet one flies off to infinity and the other one stays small. So they're asking this question, is there a pattern to the Mandelbrot set? That's what we're asking. There's one more complication, and then we'll get to the really cool stuff. Okay, the one additional complication is that the Mandelbrot set also includes what we call complex and imaginary numbers. And I hate the name imaginary because it makes it sound like they don't exist, like we made them up. That's not the case. They do exist. They are perfectly legitimate. But an imaginary number is a number that when you square it, you get a negative. And the sort of basic unit of the imaginary number we represent with the lowercase I, And I squared, by definition, is equal to -1. And that bothers people, because how do we have a number that when you square it, you get a negative? Imaginary numbers can't be positive, because a positive number, when you square it, you get a positive number. And yet imaginary numbers cannot be negative, because when you square a negative number, you get a positive number. Furthermore, they can't be 0, because 0 squared is 0. So how do we have a number that's not positive, it's not negative, and it's not 0? That's a little hard for a lot of people to grasp. It's kind of, but you know what? It's experience. It's like when you're a little kid. When you're a little kid, negative numbers bothered you. You say, well, I can have 1 apple or 2 apples. I don't understand how I can have -3 apples. That doesn't make sense, right? But then you get a little older, you get a bank account, suddenly negative numbers make a lot of sense, right? Yeah. Yes, I can have less than nothing. Okay. It's the same way with the so-called imaginary numbers. It's just that most adults never gain experience with that, so they remain counterintuitive. But there are numbers that exist that are not positive, they're not negative, and they're not 0. How do we imagine these? How do we think about them? Well, one way to do it would be this. If you consider a number line. So you got the positive numbers to the right of 0. You got the negative numbers to the left of 0. Then you got 0. Now, imaginary numbers are not positive, so they can't be to the right of 0. And they're not negative, so they can't be to the left of 0. And they're not 0. Where would we put a negative number? How about up there? It's not to the right of 0. It's directly above it. It's not to the left of 0. And yet it's not 0 because it's above it. So you can think of the imaginary numbers as being along a different axis. And you can multiply I, which is the square root of -1, by any of the, well, to add insult to injury, we call the other numbers real. Again, it's just a name. So you got the real numbers along that axis, the imaginary numbers along that axis. They equally exist. They're equally true to the mind of God. But you can multiply any of the imaginary number by a real number and get other imaginary numbers along that axis. So you can have 2i and 3i and so on. Okay? And they work just like any other numbers. Just remember, when you square I, you get -1. So, for example, if I had 3i and I squared it, that would be -9. Okay? That's how it works. You can also have numbers that are off axis. These are called complex numbers. They have a real component and an imaginary component. So 1 plus 1/2 I, that's one number. It has a real component, which indicates its x position, and it has an imaginary component, which represents the y coordinate. Does that make sense? So it's kind of neat, because you can represent any point on a plane with one number. The real component representing its x value, and the imaginary component representing the y value. Okay, so the Mandelbrot set includes these complex numbers, and what we can do is we can make a map of which numbers belong to the Mandelbrot set, because remember, it's not intuitive. You just look at a number, you can't tell. You got to run it through that formula, and we're curious to see if there's a pattern, if there's some kind of, is it just going to look crazy? Is it just kind of random, or is there going to be a pattern there? Well, it turns out we can have the computer check each point, because they can do it quickly. They can run it through that formula and see if it gets big or see if it stays small. And what we'll do is we'll take the points that belong to the Mandelbrot set and we'll color them black. We checked -1. Remember, -1, when you saw the sequence of Z, it was -1, 0, -1, 0. So it stayed small. So it's part of the Mandelbrot set. So it gets colored black. 0 just generates a sequence of zeros, so it belongs. And then numbers that, as we check more of these, we're going to find that these ones also belong. So it does look like there's a pattern there. There is a pattern. But it's not a simple pattern that we might expect. And then the numbers that don't belong, we'll give them a different color, like red. And remember, we checked 1, and we saw, remember, it got real big real quick. So 1 does not belong to the Mandelbrot set. And as we check other numbers, we find that these ones don't belong as well. Okay, so we're just basically taking each of those numbers, which has a real component and an imaginary component, and running it through that little formula, and the computer's doing it for us, so it's fast. And as we do this with more and more points, we find a shape emerges. And the shape is not something that anyone was expecting. The shape that emerges is this. As you check more and more points, that's the shape you get. This is a map of which numbers belong to the Mandelbrot set. And what the computer's done is it's just gone along systematically and checked each point, and that's the shape that results. Remarkable. And nobody was expecting this. This was discovered in around 1980. That was the first time that computers were fast enough to be able to check these points efficiently and plot the result. And so basically the points that are black here, so 1/2 eye, is that part of the Mandelbrot set? You can see, yes it is. It's colored black. The computer checked it and the sequence of Z remains small. So now we don't have to run it through that formula. We now have a map. And the interesting thing isn't so much that we have a map, but the shape of the map is remarkable and something no one was expecting. And remember, points that do not belong, we colored those red, and I even shaded it. So points where the sequence of Z gets really big really fast, meaning they're far away from the Mandelbrot set, I gave them a dark red color. And if they get big but they do so slowly, I gave them a brighter color like yellow. So yellow represents points that are very close to being on the Mandelbrot set, but they're not quite. Okay? And then the points that are on it are black by convention. You can pick any color for points of the exterior, but by convention, points that belong are colored black. So there you go. And so you can see that we can check now. We can see -1. Yep, that certainly belongs. 1 doesn't. 1/2 doesn't. The last point on the real axis that does belong is 1/4. That's where it shifts. And anyway, so you can see which points belong. Now, and I'm going to remove the grid because you know what this means now. This is just a map of which points belong. But we want to explore this shape because this is a shape no one was expecting. And you have several features. The most obvious feature is this large heart shape, which is called a cardioid. Now, a cardioid is what happens when you take a circle and you roll it around another circle of equal size, keeping your pen affixed to one point on the original circle. That's a cardioid. And you can see that's the exact shape of the main section of the Mandelbrot set. Why? I have no idea. I'm sure there's a reason, I just don't know what it is. So isn't that fascinating? Now the other shapes that pop out, probably the next largest shape would be this large circle here. And you see all kinds of circles, and they are perfect circles that are growing off the exterior of the cardioid. Like it's got a bunch of warts growing off of it or something like that. So you got the cardioid, and you got these discs, perfect circles. That one's centered right on -1. It's got a radius of 1/4, and it's really remarkable. And then the other feature that you see are these little, like lightning bolts or dendrites that are extending away from the circles. You see those little wiry features, right? And there's one that's perfectly straight, the one right here on the tail. So there you go. So that's kind of, now keep that in mind, because we're going to see the shape again, and it's pretty remarkable. Now the Mandelbrot set, this map of the Mandelbrot set, that's all it is, a map of which numbers belong, turns out to be just amazingly interesting and complex and rather beautiful. And we can zoom in on portions of it by having the computer plot points at smaller scales, and we can zoom in on it. And we find, for example, that when you take a look at these circles, this circle, which has a circle growing off of it, which has a circle growing off it, which has another circle growing off of it, and so on, and it forms this tree trunk, and then it branches into 2 for a total of 1, 2, 3, right? See that? Now the next one down on the left, you can see it branches out 1, 2, 3, 4, including the trunk, 5. See that? Now if we go to the next one down, it's 7. They're getting smaller and harder to see. And then 9, 11, 13, 15, 17. It knows how to count by 2s. It's adding 2 to each. And they go off to infinity, odd infinity, whatever that means. They get smaller and smaller. They never end. And each circle gains 2 additional limbs for whatever reason. Isn't that fascinating? Again, nobody was expecting this, but there it is. Now, if we go off to the right, you count the number of, on this one, it's 1, 2, 3, 4, right? And the next one's 5, 6, 7. So you have the odd numbers on the left, and you have all the numbers, beginning with 3, on the right, evens and odds. So somehow this shape, the Mandelbrot set somehow knows how to add. It's kind of remarkable. How to count. 3, 4, 5, 6, 7, 8, 9, and so on. Isn't that wild? And it gets even cooler because, of course, if you take 5 plus 3, that equals 8, right? And lo and behold, the one in between those two has 8. And that's true of all of them. All of them add the numbers of the next 2 large ones there. You take any 2 and you see the next largest one in between them, and it adds the number of dendrites. Isn't that wild? So you could take 7 and 3, and lo and behold, that'll be 10 for every one. So the Mandelbrot, this map of the Mandelbrot set somehow knows how to add these little dendrites together I mean, it's pretty remarkable that an inanimate shape knows how to count and add. Pretty amazing. A lot of mathematical properties. One of the coolest aspects of the Mandelbrot set, though, is what we're going to take a look at now. Again, you have keep in mind the overall shape, the cardioid, the main disc, you got other circles growing off of it, you got a spike there at the end, and then you got this little bump on the spike there. So let's zoom in on that by replotting this at smaller scales, which we can do, and we find that it's a smaller version of the original. Isn't that wild? Same overall shape, you got the cardioid, you got the main disc, circles growing off of it, and a spike. And the only difference is on the exterior, there's extra spikes growing off of it. We zoomed in on a spike, and the baby version has extra spikes. We're going to find that's significant. And you might notice that this little baby version, on its spike, it's got a little bump there. What could that possibly be? Well, it's another one. How about that? So this is the grandbaby, and he's got extra spikes growing off of the exterior, but the overall shape's the same. And of course, the grandbaby has a little thing there growing on it. What could that be? Well, yeah. Now this goes on forever. You can do that forever. It's got an infinite number of babies growing on the tail. Each one of those has an infinite number growing off of their tails and so on. Isn't that remarkable? Yeah. Now a shape like this that has smaller versions of itself built in is called a fractal. So this is an example of a fractal. One that's built into numbers that we didn't know about until 1980. Pretty remarkable. So look how small the grandbaby is, or the great-grandbaby, I guess, compared to the original. And in case you're wondering, there's no larger one. This is the atom. Okay, this is the first, and all the other ones extend off of that. But the fractal nature of this is not limited to the overall shape. You're going to find that if you zoom in on pieces of this, the pieces tend to have a fractal quality as well. So we could zoom in on some of these shapes and continue to zoom in on them and continue to zoom in on them. And you think, well, it's going to stop at some point, but it never does. This shape is infinitely complex. It's infinitely wiggly, if you will. It's as wiggly as is possible in 2 dimensions in terms of the way it wraps around and so on. Isn't that not amazing? I mean, it's just kind of mind-boggling. And I should explain what's going on here, because remember, I told you that dark red means it's far away from the Mandelbrot set. The sequence of Z got big fast. Bright yellow means it's really close. And you might say, but it doesn't look like it's close, because black would be on the set. It doesn't look like it's close to anything black. Well, it is. It has to be, because it's bright yellow. It's just that what you're seeing here, there's actually a black thread that's wrapping around. It's just so tiny, it's smaller than a pixel, so the computer's not showing it. So there is, in fact, a black thread that's wiggling around that's making that shape. It's just we're seeing the points that are very close to being on that. But you could zoom, if you zoom in eventually, there would be black spots on that. So pretty remarkable. So now what's fun to do is just kind of explore this shape that the Lord has planted into numbers from creation that we only knew about in the 1980s. And one of the places that's fun to explore, we call it the Valley of the Seahorses. It's the valley in between the cardioid and the main disc. And it's because on the right side it looks like seahorses. They're upside down. But doesn't that look like seahorses there? Yeah. Now the colors are arbitrary, other than by convention, black means it belongs to the set. So we'll change the colors every now and then to keep things interesting. And some certain colors bring out certain features too. So let's go and see what these seahorses look like when we zoom in on them. Really quite beautiful to think that we're just looking at a map of which numbers belong to the Mandelbrot set, and the map is beautiful. It's beautiful. And again, these bright points right here, bright means it's close to the Mandelbrot set, so that means there must be a thin black thread that's stemming off of that and wiggling around and making all this incredible structure. And so you have this kind of like spiderweb structure there. Pretty amazing. And so we can zoom in on that, see what that spiderweb's made of. Kind of interesting. Now I found from experience, if you zoom in on the center of that, you can do it the rest of your life. It just continues. And it doesn't change very much. It looks similar to the overall shape. So let's go off axis and see what these spiderweb strands are made of. Let's check those out. And they're made of smaller spiderwebs. So again, you have that fractal quality to them. Quite remarkable. Okay, and so the bright yellow means it's really close to being on the Mandelbrot set. So there's a black spot there, no doubt, and it's wiggling around and making these wonderful structures. And we again see mathematical properties here because you can see there's the central hub of this spider web. There's one there and there's one there, and they kind of collide in the middle, and they make 4. 1, 2, 3, 4. And as we zoom in, you'll find it'll go from 4 to 8 to 16 to 32, 64, 120. It's all the powers of 2. Interesting. So it knows how to multiply, too. It can count, it can add, and it can multiply. And if we zoom in on that center there, you can see it going from 4 to 8 to 16 and so on. And in the middle is, lo and behold, another little baby version. How about that? Now this time we zoomed in on a spider web, and the baby version has extra spider webs growing off of its exterior. That's a common feature. Whatever part of the Mandelbrot set you zoom in on, if you find a baby there, it will have extra stuff growing off of it that resembles the section of the parent that it grows off of. But this is just a tiny little section of the Mandelbrot set that resembles the overall set. But we're zoomed in by a factor of, I don't know what it is, probably more than 1 billion. It's just a very tiny little section of the original. And of course, it has a spike, and you can see it's got a little baby version there, just like the original does. And look how small this is, though, compared to the original as we zoom back out. Look how tiny it is. And there's an infinite number of those. Isn't that amazing? Gives you a little glimpse into the mind of God. Because the mind of God is what's responsible for numbers and laws of mathematics that determine the relationship between them. No human being made this. Now this time we'll go off to the left. So this is the same valley, but we'll go to the left this time. They call it the Valley of the Double Spirals. I love these. I think they're beautiful. They remind me of spiral galaxies. They are double spirals because this strand, if you follow it around, oh, there's one in between. So this strand and that strand are the same, and that strand and that strand are the same, but they're different from the other. So it's 2 strands wrapped around each other. It's a double spiral. It's stunningly beautiful. And if we zoom in, again, the center, you can zoom in on the center. It goes on forever. So we'll go off to the side, and you get these beautiful structures. Again, you're just looking at a map of which points belong to z squared plus c. That's what you're seeing. And we plug numbers into that. We find that numbers are amazing. They have beauty built into them. And you'll see here we find more double spirals that resemble the original. See, there's a double spiral there. There's one there. There's one there. We find spiderweb type structures. And we have these little shapes here too. I call them bow ties because they remind me of a little bow tie there, where you have 2 double spirals that collide in the middle. And I find them to be very, very beautiful when you zoom in on them. Isn't that nice? Isn't that pretty? And so you have, again, you have a double spiral here, 1, 2, and then it goes to 4. There's 1, 2, 3, 4 double spirals there, to 8, to 16, 32, and so on. And when you go into the middle, you're not surprised this time, but there it is. There it is, a little baby version. And so you see here, you go 1, 2, 3, 4, 5, 6, 7, 8. The next one, 1, 2, 3, 4, would be 16. And then 32, 64, and so on. Forever. It goes on forever. All the powers of 2. Might that have something to do with the fact that this is z squared plus c? Could be. But isn't that amazing? So that we see a baby version. This time we zoomed in on a double spiral, and we find the baby version has double spirals growing off of it. Again, each one of those represents a black thread that's going out through and wiggling around, making that incredibly complex and beautiful shape. Pretty amazing. Did any of you have any idea this was built into numbers? No. Nobody did before 1980. Only God. Another valley that's fun to explore. Basically, the real pretty stuff I found is in the valleys. That's where you find the pretty stuff. And the other one we're going to explore is this valley right here, the main one on the cardioid. And this is called the Valley of the Elephants. You'll see why when we zoom in here. See the elephants there, one after the other, marching along. And here they're hanging from the ceiling, okay? So they do look like elephants. There's an infinite number of them. They get smaller and smaller as you go in. So there's actually an infinite number of elephants there. And let's just zoom in on a couple of them here. Each one, you have these circle. Each one is standing on one of these circles, right? Like an elephant at a circus standing on a ball like that. So there you go. Each circle has one elephant. Keep that in mind because that'll be important later. Each circle has one elephant growing off of it. And the elephants have a trunk, the trunk that kind of curls in on itself. And I found the deeper you zoom into the valley, the elephants get smaller and their trunks get curlier. They actually get tighter and tighter. It's kind of interesting. So let's zoom in on that spiral. It is a single spiral. We had double spirals before, where you had 2 strands wrapping around each other. This is a single spiral. It's one strand. See that strand? If you follow it around, there's nothing in between it. So it's a single strand. And if we zoom in on it, what kind of shapes do we get? Well, you certainly get beauty. You get little bow ties. This time they're made of single spirals because we zoomed in on a single spiral. And if we continue in, we find that same pattern. It goes from 1, 2 to 4 to 8 to 16. And I found that whenever you zoom in on the middle of those, you find in the middle a little baby version. Now it's rotated around. We zoomed in on a spiral and it got kind of spun around, but there it is. Isn't that amazing? The structure of this, the beauty of it, built into numbers, revealed by that little formula, z squared plus c. The numbers that belong to it, that's their map. It's mind-blowing. And the fact is, it's infinite too. You could zoom in on this forever. You can see it's got a little baby version right there. But even this baby version, it has a valley of seahorses and a valley of double spirals. And you could zoom in on that, you see. So not only does the Mandelbrot have an infinite number of babies, but each baby has an infinite number of babies. It's an infinity of infinities. And that, again, so God's not only infinite, his mind is infinitely infinite. That'll keep you awake at night. All revealed, that's just a map of which numbers belong to that formula, where z stays small when you plot it. Pretty amazing. And you could spend, because it's infinite, you could spend the rest of your life exploring that shape and you would only scratch the surface because it's infinite. You could zoom in on it forever. And there, you can find on the internet, you can find Mandelbrot deep zooms where they'll zoom in by a factor of like a Google, which is 10 to the power of 100. And it's astonishing. And it has detail and beauty at all levels, just like God. But then that made me wonder, well, that's just one equation. What happens if you change the equation? We get another shape. How about that? So that's the Mandelbrot. We call this a multibrot because it's a multiple. I changed the power from z squared to z cubed. I find if you change c and make it like 2c or c divided by 2, it just changes the size of it, or you can rotate it and things like that. It doesn't change the shape you get. But if you change the power, you get a different shape. And the interesting thing about this is everything's gone up by 1. Because the Mandelbrot has 1 valley in the cardioid. This has 2, 1, 2. The Mandelbrot has circles attached to it which have no valleys. This has cardioids, each of which has 1 valley. Everything goes up by 1. Some things go up by 4, in any case. So this is our new shape here. And it's what happens, it's called a nephroid. A nephroid is what happens when you take a circle half the size of the original and roll it around, keeping your pin affixed to one point on the smaller circle. And you can see that's exactly what shape it is. It's a nephroid. Isn't that fascinating? And instead of circles growing off of it, it's cardioids. We've seen that shape before. So no more circles, all cardioids now. And I found too, it's fun, you can change the power incrementally. You can go z to 2.001, z to 2.002, and plot the results. And you can see how one kind of morphs into the other. So that was kind of a fun little experiment to try. So there's the multibrot, and then there's the Mandelbrot there. See? So you can kind of see how things get multiplied. Kind of interesting. So intermediate powers generate cool shapes too. But is it a fractal? Well, does it? If you take a look at this, in fact, let me go back to this here. And what section of it is the least changed? What do you think? A lot of stuff's happened on the left. The thing that's the least changed, I think, is here, right? the Valley of the Elephants. So that made me wonder, do we still have elephants? So let's find out. Let's zoom in on our multi-brot, see if we still have elephants. We do. But what's interesting, remember with the Mandelbrot, one circle had one elephant, and there were an infinite number of them. Now they've doubled, because the circles have become cardioids, and the elephants have split into two. So previously we had an infinite number of elephants, and now we have twice that many. Think about that for a while. But yes, we do find elephants, and if we zoom in on them, we find a single spiral just like before. But will the other shapes be the same? Will we find little bow ties there? Let's check it out. Yeah, it's a tri-tie. It gained an extra loop. Looks like one of those little fidget spinners, right? So there you go. So it has 3 now. And if you go in, it'll go from 3 to 9 to 27. It's all the powers of 3. And if you zoom in on the middle, you find a baby version of the entire set. Isn't that amazing? So it is also a fractal. And it has baby versions too. There's one up there that you could zoom in on. So it has an infinite number of babies built into it, which means you could spend the rest of your life studying this shape and you would never scratch the surface. Because it is infinite. It'll go on forever. And you continue to find beauty at all levels. Is that not mind-blowing? All right, so that's z cubed plus c. Let's try something else. Let's try z to the 4th. There you go. You get that. And at this point, I'm starting to see a pattern. This has kind of a 2-fold symmetry, and the power is 3. This is the power of 4, and it has a 3-fold symmetry. Apparently, the symmetry is 1 less than the power. So if it goes z to the 5th, sure enough, you get a 4-fold symmetry. Z to the 6th gives you a 5-fold symmetry. And if you go z to the 7th, you can get snowflakes. How about that? Wow. And sure enough, if you zoom in on this, does it have baby snowflakes? It sure does. You can zoom in on sections of it and get baby snowflakes there. I think it's amazing. Then it occurred to me, what if we try a negative power? Now, a negative power is the reciprocal of the positive power. So z to the negative 2 is 1 over z squared. And remember, black means it does belong to the set. Colored means it doesn't. Now, it's the outside that belongs. So most of the universe, almost all the universe belongs to the set, except the interior, which does not belong. So basically, it flips it inside out, which kind of makes sense. We're taking a reciprocal. But the shape is different now. We get a very different type of shape. And if we zoom in on it, we'll find the overall shape doesn't repeat. You can't find baby versions of that little trident type structure, but it's still fractal. You'll find that sections look similar as you zoom in. And the beauty is remarkable. It looks to me like a series of overlapping pebbles, which gives it sort of a 3D appearance. But it's not. It's flat. It's just the way our eyes are programmed to understand occlusion. It makes it look like it's 3-dimensional. But if we zoom in on it, you'll find that it does go on forever. It is a fractal. Pretty neat, huh? You could do that the rest of your life too. You could spend your life exploring this shape. It's also infinite apparently. It has beauty at all levels. So that's z to the negative 2. Gives you kind of a 3-fold symmetry, but it's inside out. Z to the negative 3 gives you a 4-fold symmetry, so now it's 1 greater than the power. Z to the negative 4th, and another way to make snowflakes, z to the negative 5. Of course, they're inside out, snowflakes, but pretty neat. Okay, so what does all this mean? I mean, are we just looking at pretty shapes? What causes the beauty in fractals? What causes the complexity in them? The fact that they have these mathematical properties and that no one seems to fully understand. So let's start with the first question. What causes the beauty in the fractals? Is it the man-made color scheme? I picked the colors. I think they're nice. Some programs use horrible color schemes, and shame on them. But the fact is, the color doesn't make the beauty. Because if I take this particular fractal and I remove the color and make it grayscale, it's still beautiful. There's an inherent beauty in this structure. Now, I think the color helps enhance it. And frankly, the colors are assigned to a particular value of z, and how long it takes to escape. So they're still determined by the math. And God created color anyway, so I'm borrowing his colors. So it's not the man-made color scheme. That's not what creates the beauty. Did the computer create the beauty? Some people say, well, see, the computer made that. No, it didn't. Because remember, we checked the first few points manually. You could generate that shape by hand. The shape is determined by the numbers and laws of mathematics and the formula. Okay, so the computer didn't create that shape. It simply revealed it, and it revealed it very quickly because it can do these repeated calculations fast. That's why it wasn't until the 1980s that we discovered these shapes. But theoretically, you could plot it by hand. The shape is built into numbers. Did people make it? Did people make this shape? Well, we picked the formula, but once you pick the formula, the shape is determined by the laws of mathematics. And people didn't make the laws of mathematics. We discovered many of them. We didn't create them, right? It's not like somebody decided, you know what, 2 plus 2 should equal 4. We discovered that, but you can't make it anything different. If people decided that 2 plus 2 should equal 3, that wouldn't make it so. We don't have any control over the laws of mathematics. People did not make this. People were surprised by this. When Benoit Mandelbrot, he was the guy who started promoting these things, that's why it's named after him. He worked at IBM, and he was shocked at the beauty in these maps of formula. So the beauty is somehow built into math. It's somehow built into math. What about the complexity in fractals? Why is it that they know how to add and multiply, and when you zoom in on them, you get smaller versions, and they're infinitely complex, they're infinitely wiggly? Did the computer create it? No, the computer revealed it. Right? Microscopes don't create bacteria, they let you see them. The computer allows us to explore this shape quickly. It doesn't make it. Because the computer's just following the laws of math and plotting the result. You could do it manually if you had a long time. Did human beings create it? Hardly. It's infinite. We can't create things that are infinite. It's not like somebody decided, okay, I'm going to make this shape, it's going to look like a cardioid, and I'm going to draw an infinite number of... You don't have time. You don't have time to draw an infinite number of baby Mandelbrots. Human beings did not create this, and we were surprised by it. You wouldn't be surprised by something you created, right? You make it something, well, how about that? I had no idea it was going to look like that. Did the formula create it? Well, the formula determines the map, to be sure, but we found when we changed the formula, you find beauty in it anyway. It doesn't really matter too much what formula you pick. Any power of z, any integer power will generate these beautiful fractals. So it's not the formula that created it. The formula sort of determines the parameters, but the complexity is somehow built into math, because whatever formula you pick, you're going to get something like that. And it's beautiful, and it's complex. So the beauty of these fractals and the complexity of them is built into math. So what's math? Mathematics, the definition is the study of the relationship between numbers. Okay? What are numbers? It's kind of weird to ask these questions. We don't want you know what numbers are, 1, 2, 3, but how do you define them? The best I could find in a dictionary is that numbers are a concept of quantity. I think that's the best definition I was able to find. Numbers are a concept of quantity. So when you think about how much of something there is, that's a number. Numbers are concepts. They exist in the mind. They're abstract in nature, they're not physical. You can't touch a number. You can touch a number of something, but you can't touch the number, right? I have 3 apples. You can touch the apples, but you can't touch 3-ness because it's a concept. It exists in the mind. People say, well, no, I can, that doesn't exist in the mind. It's on the screen there. That's the number 3, right? Well, is that really the number 3? Because if it is, I just destroyed the number 3. There's no more 3 now. Right? Children will have to count 1, 2, 4 now. No, that was a representation of the number 3. It was a written numeral. Numerals are not numbers. Written numerals are how we express numbers. That's the code we use for them. And that's why you can have different code systems, right? The Romans, they have 3 vertical lines to represent 3. You can do that. We pick the code system, but the number, it was already there. So laws of math are conceptual. They exist in the mind. When we talk about, a squared plus b squared equals c squared, that's a mental concept. It has applicability to the physical world, but it itself is not physical. Laws of math are conceptual. And let's think about this. Where do laws of math come from? When we learn that a squared plus b squared equals c squared, where does that come from? Did they evolve? See, the way that secularists explain the complexity in the biological world is to say, well, it didn't start that way. Life started very simple, and then it gained complexity over the time. But you can't do that with math. You can't really do it with biology, but you certainly can't do it with math. It's not like 7 used to be 3, but then it evolved. Right? 7's always been 7, 3's always been 3. 2 plus 2 is always equal 4. That law has not evolved. Were they created by people? Some people say that. Oh, human beings, we created math. No, we discovered math. If we created it, we could have created it differently. Right? And so you could have said, well, 2 plus 2, we're going to make that equal to 3 instead of 4. Don't hire an architect who believes that. We discovered these laws, we did not create them. Did they come some people say, well, they come from the universe. But math goes beyond the universe. Math, you can do things in multiple dimensions that don't exist. Like the universe has 3 dimensions of space, 1 of time. In math, you can have 16 dimensions. Or you can have Hilbert space, which has an infinite number of dimensions, and it's meaningful. It goes beyond the universe. The universe does obey math, but that's a separate issue. I would argue laws of math stem from the mind of God. When you do math, you're thinking about concepts the way God does, if you're doing it correctly. Laws of mathematics, they're conceptual, they're universal, they're invariant, right? When the astronauts went to the moon in the 60s, there were a lot of things they were worried about because that was a complex piece of equipment, especially given the time in which it was built. But they did not worry. One of the things they were not worried about is, boy, we hope laws of math work on the moon. They assumed that they would. They assumed the laws of math are universal, that they apply everywhere. All astronomers that I've ever met assume that laws of math work the same in the Andromeda Galaxy as they do here. That 2 plus 2 equals 4, no matter where you are. And if you think about it, how do they know that? It's not like they've been to Andromeda to check. But see, from a Christian perspective, I can say, well, the reason I know that laws work the same in Andromeda is because the same God who upholds creation here upholds the Andromeda Galaxy. His mind controls everything, so of course the universe will obey the same laws of math. You see, God's thoughts are conceptual. God is omnipresent. He upholds the entire universe in a way that's consistent. God does not change with time, therefore laws of math don't change with time. God is sovereign, therefore there are no exceptions to laws of math. I can make sense of the existence and properties of laws of math because I understand the biblical God who is responsible for them. But the naturalist has a dilemma. He's got somebody who doesn't believe in God. He says the universe is all that there is. Laws of math are conceptual. They exist in the mind, but they existed before people. Because the planets orbited the sun, according to Kepler's laws, which are mathematical in nature, and they did that before people for 2 days, in my view, for billions of years in their view. How can you have math before people if math was created by people? You see the problem? Math requires a mind, and yet in the secularist view, there were no minds before life, before human beings, or at least before life forms, right? But in the biblical view, there's always been a mind, the mind of God, so it's not a problem. There are also physical fractals. The fractals we've looked at so far, you can't touch them because they exist in the mind. We looked at plots of them, but those are abstractions, right? They don't exist physically. But there are fractals that are made up of atoms that you can touch. They don't go on forever because atoms are little spheres. But nonetheless, there are things in nature that are approximate fractals, like snowflakes. Snowflakes are fractal. You zoom in on them, you get a smaller version of the original. Maybe not exactly, but that six-fold symmetry, which is determined by the properties of the water molecule and so on. These little gems from heaven, they're beautiful and they're fractal in nature. That stuff that grows on your windows in the winter, that I always thought was kind of amazing, it's fractal in nature. You zoom in on it, you get smaller versions of the original in many cases. Ferns are fractal in nature. They have a branch, then it branches off into other branches, and they branch off into smaller branches, and they branch off into smaller branches, each of which resembles in some way the original. I even found fractal broccoli. So I guess broccoli is good for something after all. See that? See, it's a cone, but it's made up of smaller cones, which are made up of smaller cones, which are made up of smaller cones. Pretty neat. The way coastlines are, they're fractal. Mountaintops, the way they branch, fractal. Clouds, fractal. Lightning bolts, the way they branch into smaller branches and branch into smaller branches, fractal. Pretty amazing. It's even more amazing when you watch it in super slow motion. You can see how it branches until the leader connects and then most of the current goes down the leader. Pretty amazing. All fractal. Why? Why do fractals occur both in math and the physical world? That's the question. Now, some would answer and say, well, Yeah, well, before I get to that, let me show you some examples of this. That is a multibrot. That's z to the 7th plus c. That you can't touch, but that you can. That's math. It exists in the mind. That exists in the world, physically. That is part of the Mandelbrot set. It doesn't exist physically. It's not made up of atoms, but that is. That may look like a plant, but that's actually a mathematical graph called a Barnsley fern, where each leaf is the entire fern. See? I'll do that again because it's cool. Look at that. Isn't that neat? Each leaf is the entire thing. And that resembles ferns. So that's a mathematical graph, but that's made of atoms. That shape doesn't exist in the physical world. That one does. That shape is a mathematical graph. It does not exist physically. This, unfortunately, does. That shape, part of the Mandelbrot set. It's a double spiral. You can't see that in a telescope because it doesn't exist physically, but that you can. How about that? So why is it that fractals occur both in math and the physical world? Now, one answer is that, well, the physical universe obeys math. Okay, so if fractals can occur in math, it stands to reason they can occur physically, and that's a good answer as far as it goes. But then I'm going to ask, but why is it that the physical universe obeys math? Math's conceptual. It exists in the mind. How does the universe know to obey my mind? Well, if my mind were the source of math, that would be a problem. But see, I would argue that math is a reflection of God's thinking. God upholds the universe, and so of course the universe will be mathematical because God is. The mind of God is responsible for laws of mathematics. The mind of God is responsible for upholding the universe, so it follows the universe will be upheld mathematically. Makes sense as a Christian. But how would a secularist answer that? I don't think they can. They know that the universe does obey laws of math, but they can't explain why there are laws of math if there's no lawgiver. They can't explain why the laws of math have the properties that they have, like universal invariant, or how they could possibly know that. They can't explain why the universe is compelled to obey them. And if you think they can, ask them. Ask a secularist. Why is it the physical universe obeys mathematical laws? Because I have to tell you, there was a brilliant physicist, Dr. Eugene Wigner, Nobel Prize-winning PhD physicist. Brilliant mind. Brilliant. But apparently not Christian. And he wrote a wonderful article called The Unreasonable Effectiveness of Mathematics in the Natural Sciences, where he ponders this question: why is it the physical universe obeys math, which is conceptual? He says it's difficult to avoid the impression that a miracle confronts us here, or the two miracles of the existence of laws of nature and of the human mind's capacity to divine them. He says it's amazing enough there are laws of nature. What's even more amazing is they're made of math. They're as if human beings, this math that we human beings have discovered, the universe obeys them. Why is that? You want to see his conclusion? From one of the most brilliant men in the world, but from a non-Christian perspective. The miracle of the appropriateness of the language of mathematics for the formulation of laws of physics is a wonderful gift which we neither understand nor deserve. His answer is, we don't have an answer. And secularists who say, oh, I think there's an answer to that, they haven't pondered this. This guy pondered it. He thought about it, and he's brilliant. But you see, there is no answer in the secular worldview. Everything we've seen today makes no sense in a secular universe, where there's no God upholding the universe in a consistent way. Why would there be laws of mathematics in a chance universe? Why would the universe feel compelled to obey them? You cannot account for that in a secular worldview. So we've seen that beauty of infinite complexity is built into numbers, right? Numbers are abstract conceptions of quantity. They exist in the mind. Concepts require a mind. Numbers are a reflection of the way God thinks. We can make sense of what we've seen today as a glimpse into the way God thinks about things. That's why it's beautiful. That's why fractals are beautiful, because they reflect God's nature in some way. The secular worldview cannot account for the existence and properties of numbers or mathematical truths. Numbers existed before people, yet they are conceptions. They require a mind, but you don't have minds in the secular view before people. So laws of mathematics, they're universal. They apply everywhere. They're invariant. They don't change with time, because God doesn't. God's omnipresent. He doesn't change with time. And so his thinking is reflected in these laws of mathematics. Now, the physical world contains fractals. I can make sense of that. The secular worldview can't account for that. Why the physical universe obeys math? I can, because the universe is controlled by the mind of God, the same mind that is responsible for mathematical truths. So you can get all of this on the DVD, Secret Code of Creation. We have it on Blu-ray too, because it's very pretty, as you've seen. And we have a book on this too, called Fractals, the Secret Code of Creation. And I think you'll really enjoy that. I get to go into some of these other shapes and some other formulas that I haven't explored today. And the cool thing is, if you get this from us here, we've included a CD with software on it, the software I use to plot these shapes. And so you can explore these too. In fact, all the pictures in the book are on the CD. You can drop them into the program and continue to zoom in if you want to see what they're made of. So it's a fun feature. Again, ultimate proof of creation gives you a bulletproof argument for biblical creation. I won't go through all these because we've seen these before, but do remember that we have the library pack if you want to get kind of the best of everything. And don't forget to sign up for our monthly newsletter. Make sure you put your email address. It is an electronic newsletter. So if you don't put your email address, you'll get nothing. And do check us out on the web as well, biblicalscienceinstitute.com. Thank you very much. God bless.
Was he going a little fast at the end there? Yeah, he's running out of time, but hey, check out the book table. They sold a lot of stuff, so there's just 2 tables now out there instead of 4. And remember that the kids' stuff is 20% off. I don't know if they still have stuff left on dinosaurs or not, but check that out. I love that God designed math. And I can think of other examples. So Lauren Heinley, one of our assistant pastors here, made the tables in our fellowship room downstairs. And you should check them out. In fact, while you're eating lunch, you can sit down there if you want to. And those tables are beautiful live edge lumber. He finished them beautifully, the designs and everything. And he pointed out to me when he made them that, this beauty was inside of a tree out in the middle of the forest somewhere, and nobody even would have ever known it if they hadn't cut the tree down, sliced it open, and seen that beauty that was in there. And the forest is filled with those trees. All that beauty concealed in all those trees. Just amazing. You want another example of that? Check out the granite kitchen countertop we have downstairs, which came from some rock that they dug up somewhere. I think that stuff comes from Vermont, doesn't it, Mike? Most of that granite? But I'm not sure where it came from, but I know it came out of the ground. And if you look at the design in that granite, and you think they just sliced this out of a rock that was in the ground somewhere, and God put all that beauty. Put it in mathematics. Mathematics, like Jason said, was not invented. It's not a product of man. It's something that was discovered. And all these designs and patterns just blow your mind, and they speak to a creator. And that's why I think it's so important to do this kind of stuff. So as I said, his materials are out there. Jason will be back here tomorrow morning. He's going to finish out the conference tomorrow with a talk on the importance of Genesis. So if you're not a regular part of Calvary Chapel Marlton, we don't want you to miss your own church. You can watch tomorrow's service and anything you saw this morning all on our YouTube channel. So when you press play, if it begins with the announcements, you can just skip over those and get right to the message that you want to hear. So sometime this week, you could catch his talk that he's going to give here tomorrow. And make sure you tell your friends. We'd love to see those YouTube views just keep climbing. And you can buy all this stuff, but Jason said he didn't mind that we put it on YouTube because he wants people to be able to get it. So tell your friends about it. We're going to have one closing song. When we're done, the food will be outside. You're going to approach the food tent from the far side, so walk out behind it. You come back towards the food tent. There's a table there facing Main Street where the tacos are, and you take your tacos, and then some people go to the right and some to the left. There are 2 identical tables on the side with the toppings and trimmings and other things, so we can move everybody through faster. So just start at the far end. So Lord, we pray as we close today, we thank you for Jason being able to come here this morning and to share this great and awesome truth, Lord. And how far this world has fallen, Lord. How much trouble man will go to just to deny your existence. to great extremes, to deny everything just because they don't want to acknowledge you as Savior. Well, we thank you, Lord, that you have chosen to save each and every one of us. We thank you that you work in our lives to make us more like you. We pray that we could be strengthened and encouraged in our faith by this kind of stuff, that we could share it with others, maybe get their little minds turning there. Jason said earlier, some people don't use all their brains. Maybe we can get some people to use their brains by showing them some of this stuff. Maybe a little light bulb will go on in their head. Wow, there really is a God. Isn't that amazing? We thank you for the evidence that you put into the world, Lord, the evidence of design, creation, the flood, the evidence in math. The heavens declare the glory, your glory, Lord. Night after night, they pour forth speech. And there's no language that doesn't understand that. We thank you for that. We thank you for being part of your plan, Lord. And we thank you for the food also and the time of fellowship that we can share here together. Be with us. Encourage us, Lord. Thank you for providing for us. In Jesus' name. And everybody said, Amen. Amen. Somebody was asking about a Q&A. We really don't have time for that, but Jason's not going anywhere right away. So if you have a Q and you want the A, come on down front here and talk to Jason. But right now we're going to have one closing song, okay?
One, two. Let's bow before an awesome God, amen, and give him the glory. The splendor of the King, clothed in majesty, let all the earth rejoice, and all the earth rejoice. He wraps himself in light, for darkness tries to hide. It trembles at his voice, trembles at his voice. How great is our God? Sing with me, how great is our God? Oh, sing how great is our God. Next to which he stands, for time is in his hands, beginning and the end, beginning and the end. The Godhead three in one, Father, Spirit, Son. You're the Lion and the Lamb, the Lion and the Lamb. heart will sing how great is our God.
Amen. Love you guys. Be blessed. Looking forward to seeing you.